Components of a tensor. In this video, we are going to define the components of a tensor and teach you how to derive these components for a specific tensor. For instance, how to define the tensor of a rigid body rotation and derive its components. If you are interested in this subject, please subscribe to our channel to be informed as soon as a video is uploaded. Your comments help us continuously improve our channel, and your likes inspire us to create even more impactful content. The components of a vector are influenced by the base vectors used to describe the vector. The same holds for tensors. Let E1, E2, and E3 be unit vectors of a rectangular Cartesian coordinate system. Under a transformation T, TE1 is equal to T11 E1 plus T21 E2 plus T31 E3, and so on. We can write this set of equations as TEI equals TJI EJ. The components Tij in the preceding equations are defined as the components of the tensor T. The components of T can be put in a matrix called the matrix of the tensor T. This should be mentioned that these components are derived with respect to the EI basis. We note that because of the way we have chosen to denote the components of transformation of the base vectors, the elements of the first column in the matrix are components of the vector TE1. Those in the second column are the components of the vector TE2, and those in the third column are the components of TE3. Let's see some examples. Obtain the matrix for the tensor T that transforms the base vectors as follows. Let's put a reference number on the equations. Solution. Referring to equation 271. We can write the first equation as the first component is T11, the second one T21, and the third one T31. We proceed with the second and third equations. Now we can construct the matrix for the tensor T. Note how to place the components into the matrix. Let's see another example. Let T transform every vector into its mirror image with respect to a fixed plane. If E1 is normal to the reflection plane, E2 and E3 are parallel to this plane, find a matrix of T. Let's consider this as a mirror plane. E1 is normal to it, and E2 and E3 are on the mirror plane. The reflection of E1 is minus E1. E2 and E3 are not altered because they are on the mirror plane. Let's write down these notes. Now, as in the previous example, we extract the matrix of the tensor from equations 271 and 273. This is only one of the infinitely many matrices of the tensor T. Each depends on a particular choice of base vectors. Now, what if we choose a different basis? Find the matrix of T if we choose E'1 and E'2 to be on a plane perpendicular to the mirror, with each making 45 degrees with the mirror, and E'3 pointing straight out from the paper. Suppose this as mirror plane. E'1 and E'2 make 45 degrees with mirror plane. The reflection of E'2 coincides with E'1, and the reflection of E'1 coincides with E'2. E'3 is not altered because it is on the mirror plane. Again, by writing down the equations, we can construct the transformation matrix. We denote the matrix of tensor T with respect to the basis EI by either bracket T or bracket Tij, and with respect to the basis E'(i) by either bracket T' or bracket T'ij. The last two matrices shouldn't be confused with bracket T', which represents the matrix of the tensor T' with respect to the basis EI, not the matrix of T with respect to the prime basis E'(i). Another example. Let R correspond to a right-hand rotation of a rigid body about the x3 axis by an angle theta. Find a matrix of R. From figure, it is clear that RE1 equals cosine theta E1 plus sine theta E2. RE2 equals minus sine theta E1 plus cosine theta E2. RE3 equals E3. Now we can construct a matrix of the tensor R as before. Let's see another example. Obtain the matrix for the tensor T which transforms the base vectors as follows. The first equation forms the first column, the second equation forms the second column, and the third equation forms the third column. This example emphasizes again the convention we use to write the matrix of a tensor. The reason for this choice of convention will become obvious in the next section. We know that dot product of E1 and E2, E2 and E3, E1 and E3 are equal to 0. Because they are mutually perpendicular, it is concluded from equation 271. We can write dot product of E1, TE1 as, and after some simplification, it is equal to T11. This also applies to other components. Therefore, Tij equals dot product of Ei and Tej. Note again that the components of a tensor depend on the coordinate systems through the set of the base vectors. Thus, T'Ij is equal to dot product of E'(i) and T'Ej. Recall that T'Ij are components of T with respect to basis E'(i). Note that vectors and tensors are independent of coordinate systems, but their components are dependent on the coordinate systems. In the next session, I will teach you the components of a transform vector. Please subscribe my channel.